Hi everyone, it's Mr. H here. The first part of this video we got into time dilation, and the second part, that's day 2, is going to look more at the simultaneity of events and the length contraction. So let's first consider Einstein's two postulates that we wrapped up with in the last lesson. All physical laws must be equally valid in all inertial, non-accelerating frames of reference. So this only applies to non-accelerating frames of reference. And secondly, we could say that the speed limit of the universe is c. Nobody can see anything faster than the speed of c. That's always going to be the limit. We concluded as well that moving clocks ran slow and that light does not need a medium to travel through. Well, what does simultaneity mean? I want us to consider the following picture. We have a railway flat car here, and Adam and Betty are both standing on that flat car, and in between them is a light bulb shining in the middle, equal distance from each of them. And in what you see right now is they're both looking like the same picture, but we're going to, for the second picture, adapt a couple things. We're going to bring in Carl and David. So what we're going to do is we're going to put Carl standing here at rest. So here's Carl at rest. But we're now going to move this train car. This train car we're going to move at speed v. And David, well, he's really quick. He actually makes some pretty good time on his feet, and he goes twice as fast as the train car. So what are we actually going to see playing out here with this picture? Well, Carl, looking at the train car, sees Betty move away from the point source of light. He sees Adam moving towards the point source of light. So Carl has to conclude that it takes longer for the light to reach Betty than to reach Adam. It takes longer for the light to reach Betty than Adam. Okay, well that's a fairly straightforward conclusion. Now let's bring David's perspective into play. David is moving at 2v, so he's moving twice as fast as the railway flat car. He sees the cart, or car, moving left at a speed v relative to him. Because he's moving 2v, it looks like the car is moving further and further away from him. Although the car is moving towards him, it's moving further and further away from him because of his speed. So Adam is moving away from the light flash, and Betty is moving toward the light flash from his perspective. David, well, he concludes it takes longer for the light to reach Adam than Betty. And this is exactly what Einstein would have done in these thought experiments. It takes longer for the light to reach Adam than Betty. This was something that they can't really test in his time, and so he really had to do a lot with just these thought experiments, and I think these are fairly logical when you just think about them yourself. Here's where the rubber hits the road. A future event in one reference frame is actually a past event in another reference frame. In case you need more thought on this, there's another video that I'm going to put in the links below this video that will point you to another way of thinking about this. But the reason that we have this idea that one reference frame can be a future event, another one a past event, is due to Einstein's postulate. If you recall, the first postulate said that all physical laws must be equally valid in all non-inertial or non-accelerating inertial frames of reference. So that does not mean that measured values like time or length need to be the same in each inertial reference frame. Time and length can be relative, as can simultaneity. And the second thing he said is that the speed limit of the universe is 3 times 10 to the 8 meters per second. It's the speed of light in a vacuum. Well, the conclusion here, it's already written above, but it's just worth noting here in this box so it's very clear for us. A future event in one reference frame can be, it's not always, but it depends what reference frame we're looking at, but it can be a past event in another reference frame. Well, if that wasn't weird enough, we now come to length contraction. length is not fixed. I want us to consider an example with Captain Quick. He's a superhero. In fact, he's the fastest superhero that ever existed, even faster than the Flash. And she can run at 2/3 the speed of light. She's carrying a flare. Here's the flare. It's lit. That flare is going to blow. It's set to explode in 1.5 times 10 to the negative 6 seconds, so a very short amount of time. She needs to place it in the bracket. So here's the wall. And on that wall is a bracket. She needs to place it in there, which will stop it from exploding. There's a distance L from the flare to the bracket of 402 meters. So distances that we would not be able to run definitely in that amount of time, much less than a minute for that matter. So this is what she's trying to do, get it in there before. Well, classically what we'd consider is that time is the distance divided by the speed. And L is the distance. And so that's 402 meters is the length from where she is now to where she needs to go. And we would divide it by the speed. It's 2/3 the speed of light, so it's 200 million instead of 300 million. And we would get a time of 2.01 times 10 to the negative 6 seconds. Now clearly that number is larger than this number up here, and therefore she can't do it. She's going to blow up. Captain Super Quick, or Superhero Captain Quick, as quick as you are, sorry you didn't save the day. However, David is in a stationary reference frame, measures a time of 2.01 times 10 to the negative 6 seconds passing before the flare blows. He claims that she can do it. Hold up, what? How can he measure a different time? Well, he sees that there's a time dilation here. So he says the time that Captain Quick is measuring is 1.5 times 10 to the negative 6 seconds, but then we have to take into account this gamma value. Remember, this whole value here was gamma. And if you put in 2/3 c, the c squared and the c squared cancel out. 2/3 squared, 1 minus 2/3 squared, and you take the square root of that, that gives you 0.7454. Take that time that Captain Quick measured and divide by that number, and you get 2.01 times 10 to the negative 6 seconds. Just in the nick of time. She can do it. David's excited. David's hopeful. This is where the tension begins. Captain Quick and the flare are in the same reference frame. The fuse burns in 1.5 times 10 to the negative 6 seconds. How did she make it? Well, here's how she made it. Her distance was actually shorter. It was not what we said classically. We said the distance was 402 meters. Her distance, just as time was affected, distance as well was affected. L is the contracted length seen by the moving observer, and L naught is the proper length measured by the observer at rest relative to the room. So the length that is actually being seen by Captain Quick is shorter than the other value. If you think about this, if we put in 1 minus this was at 0.74, so it's 0.7454 times 402 meters. That gives us the length that Captain Quick actually had to travel. Let's go ahead and calculate that. So we have L equals L naught times 1 minus v squared over c squared, which is to say that it's 402 meters times the square root of 1 minus 2/3. We've already calculated that number. We know it's 0.74, so we can just put that number in. So 0.7454, and that's a unitless number, and that gives us 300 meters. So in fact, Captain Quick's frame of reference, if we calculate the time it took, using time is equal to distance over speed, then we go 300 meters divided by a speed of 2/3 times the speed of light, which is 2.00 times 10 to the 8 meters per second. Then we get her time to be 1.50 times 10 to the negative 6 seconds, which is what we had calculated using the time dilation formula before. So if we account for the shortened length, we can use classical calculations to find the time. But in one way or another, either we have to account for the time dilation or we have to account for the shortened length. But what the reality of it is that her time was very different than the observer that was outside of the whole picture. David, who was measuring that time that was 2.01 times 10 to the negative 6 seconds. So he saw a longer time and a longer distance. But Captain Quick, shorter time, shorter distance. You can see a really cool application of this in regards to the study of muons, what they're doing in the Large Hadron Collider and other things. It's on page 480 in your textbook. I want to point out one other thing as well, though, just a thing that, again, would only happen if we could get close to the speed of light that we would see this. But let's imagine that we were a stationary observer. What we would be seeing if we were a stationary observer and assume that the closest star to us, Alpha Centauri, and the Earth were both fixed in space. They essentially are. They're not moving close to the speed of light. But let's assume they're fixed in space. If that rocket was going close to the speed of light, we would actually see that length of the rocket actually contract. Likewise, from the rocket's perspective, if you were the person on the rocket, you wouldn't see the length of that rocket contract at all, but you would see the distance from the Earth to Alpha Centauri actually shrink. And you would see, as well as you can see from the pictures, that these would physically get shortened in that horizontal direction as well. Mind-blowing stuff. Physically, that's what happens when you do the math. So to conclude, in a moving reference frame, length contracts. The key is this: the value of any measurement is tied to the frame of reference in which the measurement was taken. Change to a different inertial reference frame, and you change the measurement of length and time.